Hi, it's Miss Lenorvitz, and in the first video that you watched, we went through how to solve part A and part B of a multi-step problem around ecosystem energy. In this video, we're going to pick up from there and we're going to solve part C and part D. So to just remind ourselves, we were dealing with this situation of a rice paddy in Southeast Asia. We know that insolation energy, or the amount of energy coming in for sunlight, is 6 million calories per meter squared per day. That the gross primary productivity, or GPP, of the rice is 0.012 grams per centimeter squared per day, and the loss due to respiration is about 20%. Remember that loss is happening because of the second law of thermodynamics. We know that in a closed system, energy can neither be created nor destroyed. It can be transformed or transformed from one form to another. When it does, though, even though the amount of energy is the same, that ability to do work is reduced. So respiration reduces the ability to do work. And we also know that 1 gram of rice is equivalent to 1,000 calories. So part C of our question asks how much energy in kilocalories. So notice we're going to remember our metric prefix here, kilo meaning 1,000. So how much energy in kilocalories would be available each day to the human population that directly consumes the energy stored in a 1,000 meter squared rice paddy? Again, it's always really helpful to visualize what this problem, or what any problem, is trying to ask you. So in this case, it's asking us if people served as the primary consumers, they were directly eating the rice that was from this 1,000 meter squared rice paddy, how much energy would be available to that human population? On the right-hand side, I'll scoot me out of the way here. One of the things that I want you to just bear in mind is that rice and rice paddies are a really important part globally of our food supply system. So you may not be able to see all the colors that are represented here, but we're looking at a world map. Here's the United States, or North America right here. We're looking, the yellow and red bars indicate yellow for imports and red for exports. So you can see the US is a major exporter of rice. And the tones of gray show you how much rice consumption per capita or per person occurs in different areas around the world. And those are shown in grams per day. In the areas where you see darker gray, greater than 300 grams of rice per day. So you can actually see that much of the world's population relies on rice as their main dietary staple, or at least as a significant supplementary dietary staple. So a really important question for us to consider. You can also notice that in many parts of the world, people eat with the utensils of chopsticks rather than forks and knives and spoons necessarily, hence one of the reasons we used that recently in a simulation in class. So let's get back to the problem now that we've visualized what we're talking about. We're trying to talk about how much energy is getting transferred to people if they directly eat the rice from the rice paddy. For this problem, we are going to pull on some answers from a previous problem. So you'll remember back in part A, we needed to calculate the net primary productivity of the rice. We solved that in part A. We figured out that it's 0.96 times 10 to the negative second grams per centimeter squared per day. So again, a centimeter squared is going to be pretty tiny, about the width and length of the last section of your pinky. So that's a really small area. But we want to know for a full 1,000 meter squared rice paddy, how many calories could that provide to a population? So just as we always would, we're going to go through this problem in steps. We're going to first identify what are the pieces of information that we already know. So one of the things we need to pay attention to, of course, is going to be the question itself. And we want to solve how much energy in kilocalories would be available each day to a human population that directly consumes the energy stored in 1,000 meters squared of a rice paddy. So 1,000 meter by 1,000 meter square of a created wetland. We know that the energy in calories that primary consumers get from their food, in this case, is going to be 10% of the energy that's stored in the primary producers. In other words, 10% of the energy that's stored in that rice plant is going to be transferred to the next trophic level. So here you're applying what you know about the rule of 10 and energy transfer in ecosystems. We also know from our earlier problem, part A of this, that the NPP, the net primary productivity in this rice paddy ecosystem, is 0.96 times 10 to the negative second grams per centimeter squared per day. We also know that 1 gram of rice contains 1,000 calories, We know that the area of this rice paddy is 1,000 by 1,000 meters, or 1,000 meters squared. And we know, using our metric prefixes, that 1 kilocalorie, prefix kilo means 1,000, is 1,000 calories. So now we need to put that information together. We're really using this equation to get our answer. So we're going to take net primary productivity times 0.10 to indicate 10% of that. We have some unit conversions that we need to do though, because notice our net primary productivity is in grams per centimeter squared per day, and we really need to know kilocalories per day. So again, we're facing a little bit of dimensional analysis. So we're going to start with NPP is equal to 0.96 times 10 to the negative second grams per centimeter per day. And we're going to step by step convert that into kilocalories per day. So here, our first conversion that we're doing, and again, because this is multiplication, you could do these conversions in any order, is that we know that there are 1,000 calories in every gram. That information came directly from the question. So now we've eliminated grams and we've converted our NPP into a form of energy of calories per centimeter squared per day. Well, that tells us how much 1 centimeter squared, again, little tip of pinky by little tip pinky part of the rice paddy would be created. But we've got 1,000 meters by 1,000 meters. So the next thing that we need to do is we need to convert that into how much is there per meter squared. So we need to convert from centimeters squared into meters squared. Again, a centimeter, there are 100 centimeters in every meter. So if we're talking about a meter by a meter, we're talking about 100 centimeters by 100 centimeters, or 10,000 centimeters squared per meter squared. Now our centimeters and centimeters will cancel out, and we're going to be left in calories per meter squared per day. We're getting closer. Remember, we want to get to kilocalories. The next thing that we want to do is we want to multiply this by the size of our rice paddy. We know from the question that our rice paddy is 1,000 meters squared. So we're going to multiply by 1,000 meters squared. And then the last thing that we're going to do is we're going to convert from calories into kilocalories. 1 kilocalorie is 1,000 calories. So we use the conversion factor of 1 kilocalorie over 1 times 10 to the third calories. And that allows us to express our NPP in kilocalories per day. Scoot that over here. And I apologize, I lost the day here as far as my units, but that would be kilocalories per day. We're not done yet though, because that tells us how much energy is in the 1,000 meters squared of rice. But we want to know how much of that energy is going to be transferred to our primary consumers, which in this case are the humans. And we know that that transformation or that transfer is inefficient. Only 10% is going to get transferred. So we're going back to our original equation here. We've got NPP in the right units now, and now we need to figure out what 10% of that is. So our last step here is we're taking our NPP, 0.96 times 10 to the 5th kilocalories, and we're multiplying it by 10 to the negative 1, or by 10%. Again, easy job here if it's in scientific notation. 0.96 times 10 to the 5th times 1 times 10 to the negative 1 is going to be 0.96 times 10 to the 4th, or in appropriate scientific notation, 9.6 times 10 to the 3rd kilocalories. So this is the number of kilocalories that would be available to that human population. All right, and now we're ready for part D. Just when you thought it couldn't get more complicated, remember that humans oftentimes are omnivores. We don't often just eat at the primary consumer level, even though we're always a heterotroph. In this case, this part of the question is asking us about what if humans are a secondary consumer in this ecosystem of the rice paddy. So the question is asking us how much energy in kilocalories would be available each day to the human population if the rice calories from the 1,000 meter squared rice paddy were first fed to pigs and then the humans consumed the pigs. So for a little infographic, and again, you want to just have a mental construct of this, we're talking about the energy that's stored in the rice going from the primary producer, going to pigs, which would be our primary consumer. Remember, in that trophic level transfer, there would be a 10% energy exchange, or 10% of the energy would be transferred for the growth of the pigs. And from the pigs to the humans, pigs going primary consumer, humans in this case being a secondary consumer, again, 10% of that energy is going to be transferred from one trophic level to the next. So as we're thinking about how to solve this one, we're thinking again about energy transfer within ecosystems and that inefficiency due to the second law of thermodynamics. So how do we approach this one? Just as we have in any of the other ones, you want to start with what you know. So here's our original question. We know that the amount of energy in the secondary consumers, which in this case is the humans, is going to be equal to the energy in the primary consumers times 0.1, or in other words, it's 10% of the energy in the primary consumers. All right, we're going to borrow again from our previous answer. We know our energy from our primary consumers from part C is 9.6 times 10 to the 3 kilocalories. So 10% of that is going to be passed on from the pigs to the humans in this case. So we'll plug that into our equation here. So the energy in calories for our secondary consumers is equal to 9.6 times 10 to the third kilocalories times 1 times 10 to the negative 1. Again, this is another way to express 0.1, and the reason we're doing that multiplication is it's a 10% transfer. Again, scientific notation here is helpful to you. It saves you some steps with math. So we've got 9.6 times 10 to the third times 1 times 10 to the negative 1. We can simplify that as 9.6 times 1 times 10 to the second. Or in other words, the energy that's going to be available to the humans if they eat the pigs, which have eaten the rice, is going to be 9.6 times 10 to the second kilocalories. One of the last things you can do here is just give some consideration to at which trophic level would it be most efficient for the humans to feed in this case, and how many people could be fed if they were eating as primary consumers, so eating the rice directly, versus if they're eating as secondary consumers, where they're eating the pigs, which have in turn eaten the rice. So hopefully that gives you an idea of how to do some of those energy ecosystem problems. Again, keep in mind that you want to, when you can, use scientific notation. You want to know your metric prefixes. You want to identify all the information that you know and visualize the problem, and you want to document all of your work. Both the numbers and the units are critical both in your work and in your final answer. If you have questions, don't hesitate to reach out, and I hope you have fun practicing these problems.